Hey guys, persistent programmer over here. Today we're gonna do Leetcode problem 525 contiguous array. Okay, so I've copied the problem over here, and the problem asks, given a binary array, which means an array of only 0 and 1, find the maximum length of the contiguous subarray with equal numbers of 0 and 1. Okay, so here in this example, we can see that there is an unequal number of zeros and ones. There's 2 0 and 1 over here. So we can see that the maximum contiguous subarray. Okay, so what does this mean, contiguous subarray? Contiguous means that it has to be um, right after each other. So we can't say that 0 and 0 is a contiguous subarray. It has to be 0 and 1. Right, so okay, so that's what contiguous means. And now let's look at some examples and some possible solutions to solve this problem. Okay, so one of the solutions that comes to mind is to just generate all possible subarrays. And then within those subarrays, just check, okay, is the number of ones equal to the number of zeros? So we could have a counter where we just say, okay, so we have our ones, and we just increment this counter, and then we can go to this, we can have a zero counter that just counts the zeros and then increment that zero counter, and then we just at the end check, oh, is the ones equal to the zeros? So that is one way of solving this problem. However, um, that will take a lot of time, so it's not the best approach to solve this. So whenever we are at this situation where we can avoid the time complexity being high, what we can consider is looking at some constant time solutions. So when we think of constant time, one of the data structures that come to mind is a map, right? So, or a hash map. So is there a way to take this problem and apply a hash map to make this algorithm faster? So let's explore that possibility and look at some examples of where that could work. Okay, so I will start off with a easy to understand example over here. I have put the indexes on top, and what we want to do here is we just want to put a +1 to the sum. If we were to take the sum at each position, if we saw 1, we would put a +1 with the sum, and then if we see a 0, we'll just do -1. Right, so I just want you to notice the patterns over here. So this is why we're doing this. Okay, so over here, the sum would just be 1, right? And over here is 2, 3, 4, 5. Okay, and then here is 6. And what happens when there's a 0? So if we did a -1 over here, 6 minus 1 is 5, right? So here the sum would be 5. Okay, so what I've done is I've just created a map of each of the sums, each of the partial sums that we saw, and the index. So this is the index, right? And these are the partial sums that we saw, right? Okay, so when we are over here, we can see that our partial sum is 5. And we have that recorded over here in our map. So we can see that number 5 is indexed to this 4 over here, right? So if we look at our I over here, if we were going in a for loop, we can see that our I index is 6. So this is just a normal for loop. And we can see that the index we stored at this position is 4, right? So if I is 6 and this index is 4, right, we can find the distance between these two indexes by just doing a minus. So 6 minus 4, right? So equal to 2. And if we look over here, our maximum contiguous subarray is of length 2, right? So I just want you to think about this relationship for a bit. If you need to pause the video and just like take a break and think about this, go ahead, because it is a little bit hard to conceptualize at first, but once you get it, it makes sense. Um, all we're doing here is finding the distance between two indexes, right? This index and this index. And we just have a system over here to record all those indexes. So we have a way to go back and do this subtraction, right? So all this is from here to here is a distance that we're calculating. So that's how we can create a map, store all the sums, and then just use that map to find the distance between the two indexes. Okay, so what I've done here is I've graphed this case over here. So I put all the indexes in the x-axis over here, and I put all the sums. So we can say all of these are the sums here in the y-axis. These partial sums that we calculated at each point. Okay, and what we can see here is that at the sum 5, right? So at this 5, if we take the index over here and we also look at our last position over here at index 6, where we got the same sum, we can see that they are on the same level here, right? So why are we thinking about this, and why does this matter, right, for this problem? Okay, so the idea is that if I have the same number of zeros and ones, and if for each time that I encounter a 1, I just do a +1 to my sum, and each time I encounter a 0, I just do -1 to that sum. So what happens when I do this is these two values eventually cancel out, so I get the same sum. So what we can determine from this observation over here is that this 5 that we got at these 2 points means that we encountered an equal number of zeros and ones. So the ones were equal to the zeros, and that's one of the conditions for the problems, that we need to find a contiguous subarray with equal number of zeros and ones. Okay, so if that all makes sense, I will go through one more example before we dive into writing the code. Okay, so let's take an edge case over here, and let's say we are only given 2 elements in our array, right? So here our first partial sum would be -1, and then in the second partial sum it would be 0. So we don't have a match over here, right? So when we get, if we were to map this, it would be, so first the 0 is encountered, so we'll get a -1, and then we would map it to the 0, and then the 1 is encountered, and we just put the 0 is the sum here, so 0, and then we put the 1 index here, right? So in this specific case, we don't encounter the same sum, and if we just initialize empty map or empty dictionary, depending on what language you're using, if we just do this, then we would get the wrong distance, right? So here the distance calculated would be 1 minus 0, which is 1. And that's not correct, because here we do have an equal number of zeros and ones, and the distance, the max length should be 2 here, right? So one way we can avoid this case is to just initialize our data structure, whether it's a map or a dictionary, with the condition of 0 mapping to -1 here. So let's run through this example. So what would happen is when we get a -1, we would just add that -1 to our map here. And then this -1 would map to 0. And then when we see a 1 and we get a 0, well, the 0 already exists. So according to our formula, it would be the index of 1, so it would be 1 minus minus 1, right? So this makes a plus, so it would be 1 plus 1, which is 2. So it would give us the correct distance. So that is one edge case that we need to keep in mind when building the solution. Okay, so I'm going to do one last run through of another example before writing the code. Here we can see that we have a partial sum. So I've just outlined all the partial sums under each element in the array. And here there's a partial sum of -1, and that -1 exists in our map, and we can grab the index 0. So from this index, so from index 6, if we minus that 0, we get a maximum, we get a distance of 6 over here. And if we look at the distance from this position all the way up to here, right? So we have 3 ones and 3 zeros, and the length of this from here, from this position to this position, is 6. And this is the distance that is our contiguous subarray with the equal number of ones and zeros. So in summary, what we need to do is we need to have a system to a map or a dictionary to update that partial sum. Every time we see a 1, we're just going to add 1 to the partial sum, and if we see a 0, we're just going to minus 1. And we're going to calculate the distance between the indexes. So that's what we did over here. We took the index and we found it in the map, and we subtracted it from the previous index. And that's how we will get this distance between elements in the array, right? That's how we're going to find our contiguous subarray. And the last thing we need to do is find the max of the distance. So we can encounter this -1 at other places in the array, right? So we will get multiple distances, and we will calculate those multiple distances by using the map. But what the question asks is the longest contiguous subarray. So we need to use our max function to find the distance um, between the elements, which is of the highest length. So that's why we need to do this. All right, so if all of this makes sense, let's go ahead and start coding. Hey guys, I'm back in Leetcode, and the first thing I've done is I have initialized all my variables. So I've initialized the sum map, which is the system where we will use the dictionary to keep track of all our sums. And then we have the max length, which is initialized to 0, so that's what we're going to return. Let me just go ahead and write that. Return max length. And I have the distance initialized to 0 and the partial sum also initialized to 0. So I'm going to use the enumerate in this loop here, and if you don't know how to use it, let me know in the comments down below. I can create a separate video in my new series, PyBytes, how to use enumerate. But what it does is it lets you access the index of the element. So what I can say here is if my num is equal to 1, then what I'm going to do is I will increment the partial sum. So partial sum plus equals 1, right? So if we see a 1, we're just adding to our partial sum, else we will subtract from the partial sum. So partial sum minus equal to 1. Okay, so once we have that done, what we're going to do is calculate and check if that sum exists in the sum map or not. And if it does, then we're going to calculate the distance. So we can say if partial sum in sum map. Okay, then what we need to do is calculate our distance. So we'll say distance is equal to I minus the previous indexed partial sum, right? So that's what we're gonna calculate. So I minus map, we'll say sum map, and we'll check the index of the partial sum there. So this is the same example we did a walkthrough of how to calculate the distance at the current index. So that's what I is. So I is telling me where I am currently, and if that number exists, I will calculate this new distance. And then max length is going to be updated. So max length will be equal to max of the previous max length and the new distance we found. Okay, so we have covered the case if the partial sum exists in the sum map. Now we need to catch the case where if it doesn't, and we'll just populate that partial map index with our current position. So else, we can say that map, sum map at the index of partial sum is going to be equal to I. So that's how we're indexing our current position in our dictionary. So later this position can be used to calculate the distance and the max length. Okay, this actually needs to be in the for loop. So we're doing all of this while we're iterating over our list here. Okay, so this looks good. Okay, I'm gonna give it run code. Okay, awesome. Yeah, so this is the answer that we were expecting, and I will go ahead and submit. Accepted. Yay, it works. Awesome. Thanks guys. If you like this video, please go ahead and subscribe to the channel, give this video a like, and if you have a different solution, please post it in the comments below. It could be in any other language. It's just gonna help other people look at the solutions and understand and solve this problem themselves. Thanks guys. Happy coding!